Well, I think we can maybe just, I'll just say a couple of words about the program for today, and then Paolo, you can take over. So today we have, as you can see here, the timetable, two invited talks on the very hot topic right now on the mu G-2 measurement and theory perspectives. And then we have a coffee break and a session with talks on BSM. And then there will be another invited talk from LHCb. So this morning, it's basically all BSM. So Dr. Pablo Roy will be sharing the sessions and the talks. And then we will just have a closing summary here at the end around the lunchtime. Okay, so Pablo, please go ahead and you can start with the talks.
Thank you, Jose. Good morning to everyone. So we will start with Dr. Alex Tusley-Booth, currently postdoc at the University of Michigan and one of the people working hard behind the spectacular result he will present. Please, Alex, you can start sharing.
All right, thank you very much for having me. It's cool to be here. I'm Alex Tusley-Booth, and I'm going to be talking here a bit about the first measurement of the mu1 anomalous magnetic moment from Fermilab's mu1 G-2 collaboration. So I want to start off with a little bit of spoilers because everyone knows this by now, but just to sort of put you in the mindset, what we've got here is a measurement that primarily, I want to point out that it agrees with the previous measurement. You can see over here that we are well within the error bounds of the previous experiment, and they are within our error bounds. So,
I'm sorry to interrupt you. Is everyone seeing Alex's slides?
Oh. No, I can't see it.
Okay, I wasn't sure if it was my fault. Okay, so now, thank you.
Now it's okay.
Okay, you can see him now? Good. Okay, yeah, so we are well within agreement of the previous measurement, and we are still quite far from the standard model prediction. In fact, we have narrowed this, the experimental average, the world average, enough such that the discrepancy with the standard model, and I want to point out that the standard model value that I am using here comes from the 2020 G-2 theory white paper, has increased from about 3.5 sigma to 4.2 sigma. So we are increasing this discrepancy with our data. The big thing I want you to keep in mind for this whole talk is that we have a 460 part per billion uncertainty at this point. So I want you to keep this number in mind as I go on to compare other numbers to. In case you need to, the number is written down here on all the slides, just to help keep in mind. So I'm going to go over this, trying to give you a complete overview of the experiment itself. Start with a little bit about the theory going on behind the magnetic moments. I'd like to give a little bit of historical context. I think that's important that people know how long this has been in the making. I'm going to give you sort of a brief overview of how the measurement is done. We'll step through the measurements a little more in depth, and then at the end we'll come back to this 460 part per billion number and see where that's all coming from. So where do we get these magnetic moments from? So elementary particles can have an inherent angular momentum not relative to their motion called spin. And if you have a spin on a charged particle, that can lead to a magnetic moment. Important to keep in mind is that the magnetic moment of a dressed particle, that's a particle existing in real space, interacting with the vacuum, interacting with other particles, is different than the magnetic moment from a bare particle because of these interactions with the vacuum. And this causes a shift in the magnetic dipole moment. So what does a spin actually do that we care about? If you have a spin and a particle with a spin, with a magnetic moment, and you put it into an external magnetic field, and the magnetic moment and the field are not aligned, the spin will start to precess. There will be a torque on the spin, and the spin will start to precess about the magnetic field, as you can see here. And this is actually very important. This is how our measurement works. So if we inject a particle with its spin and its momentum aligned into a magnetic field, a constant magnetic field, it is going to undergo circular motion, so which is a precession of the momentum vector, and it's simultaneously going to undergo precession of the spin. If your G factor, the strength of your magnetic moment, is exactly 2, these two vectors will precess at exactly the same rate, and there will be no relative phase between the momentum and the spin. However, if your G factor is slightly larger than 2, your spin will precess just a little bit faster than your momentum, and you will accumulate a phase difference over time between the momentum and the spin vector. So I want you to keep this in mind. We'll come back to this in just a moment, but this is very important. So I'm going to briefly talk about the state of the theory here, but we have a theory talk after this, so I'm not going to talk about stuff that I'm not terribly good at. So the theory has to take into account the entire standard model, has to take into account QED, weak dynamics, and QCD, where QCD is sort of the sticking point. And that's because QCD, of course, is difficult to do. QCD is, we can't use a perturbative approach on it. Its coupling constant is greater than 1. So we have to use other techniques to sort of access what's going on in the hadronic sector with the hadronic virtual particles. So I just want to point out that the recent white paper that the theory numbers used in this talk are taken from used a data-driven dispersive approach to calculate the hadronic sector contributions, not a lattice-driven approach. So why do we care about this in the first place? Well, you can sort of see from these diagrams, just some sample diagrams, that because the magnetic moment is shifted by an interaction with a virtual particle, if we can make a precise measurement, we are sort of accessing these virtual particles by making a measurement of the muon magnetic moment. The muon is better than the electron for this. Even though the electron lasts much longer, we can keep it stable for a much longer time. We can do a much more precise measurement on it. If there's any massive particles running around in any massive virtual particles, we get an enhancement factor over the electron in the muon's magnetic moment of a factor of about 40,000. And this is the ratio of the muon mass to the electron mass squared. So a more massive on-shell particle creates a stronger coupling to massive virtual particles, which is important. Okay, just a brief history here to sort of put everything in perspective. Back in 1928, when the Dirac came up with his famous equation, this was the first time that anyone had predicted G equals 2. Classically, we would expect the spin of a charged particle to have a G factor of 1. It was not. This was a source of consternation. Dirac came along and explained G equals 2. It wasn't until 19 years later that Julian Swinger came along and came up with the first perturbative correction to the G equals 2, the famous Schwinger term, A equals alpha over 2 pi. This is the correction to the G factor for all leptons. It wasn't until 15 years later, though, that the first experiment, the first G-2 experiment at the start, muon, G-2 I should say, these are all muon numbers, came up with an experiment that was precise enough to actually see this correction to the muon, and it agreed, which was a great success. We knew that it agreed with the electron at this time, but seeing that the muon obeyed the same mechanics was great. More than 40 years later, we get to the Brookhaven experiment, which is where you first start seeing the hints of your discrepancy with the standard model that inspired us to move the same storage ring from Brookhaven to Fermilab to continue this experiment, to try to drive down the statistics, to try to nail down whether this is a real discrepancy or not. So going back to that picture, I'll show you about this accumulating phase between the momentum and the spin. If you look at the rate at which this phase accumulates, we call this the anomalous precession frequency. And if you have the right experiment, this anomalous precession frequency, the difference between the spin precession frequency and the circular motion, the cyclotron frequency of the muons in the storage ring, this rate is almost exactly proportional to the anomalous magnetic moment. This is the quantity we're trying to measure. I say nearly because there are some other things going on. There are some corrections, specifically from the fact that we have electric fields present in the ring, and this is a relativistic experiment, so of course things get complicated. We wind up with a term here that is proportional to the muon's velocity dotted into the magnetic field, and something that's proportional to the muon's velocity crossed with the electric field. You'll notice, though, that these terms, these two additional terms, can be driven to zero quite well. If you have your muon momentum and your magnetic field perpendicular, which you should in this experiment to optimize your circular motion and spin precession, this term should drop out to zero. And you'll notice here that if you choose a gamma factor, a relativistic gamma factor, appropriately, you can make this term in front of the electric field correction very small, which also lets you drive this correction down. So for the most part, we can treat our experiment, our anomalous precession frequency, as being exactly proportional to the magnetic field and the anomalous magnetic moment, and then treat these as small corrections later on. So we're going to extract a mu from our spin precession measurements. So we're just going to take that last equation and rearrange it into a form that looks like this. And I like to explain this as this is kind of the inverse of what we would consider a normal magnetic moment measurement, or sorry, a normal magnetic field measurement. In a sort of a normal magnetic field measurement using optical magnetometry or NMR, what we would do is we would put some sort of sample into a magnetic field. We would measure some sort of frequency from this, whether it's a line splitting in an atomic system or whether it is a radio transition in NMR. And we would know this coupling factor here, this gyromagnetic ratio. And we would use a measured omega A and a known coupling constant to calculate B. In this case, we're sort of doing the opposite. We are going to simultaneously measure B with another system. We'll have omega A, we'll have B, and we will solve for our coupling constants. So we're going to make this complicated because, of course, simple things are no fun. And we're going to essentially have to break out what do we mean by this B field? What are we actually measuring? What we actually measure is the precession frequency of protons, and in this case, shielded protons in water, in the same magnetic field as the muons. So we wind up looking at this ratio of the anomalous precession frequency of muons and the spin precession frequency of protons in water in the same volume. And then we have to have a bunch of corrections. These are all the sort of well-known ratios known from other experiments that sort of connect this proton spin precession to the B field and to the factor of m over q that we need. So I want to point out, first thing, these additional terms that we have are very well measured quantities. And we know these to 25 parts per billion compared to this 460. This is not a limiting factor. This is, for all intents and purposes, this is quite precise for us. So we're going to measure this ratio. We're going to grab all of these ratios from CODATA, and we're going to calculate a mu. So I'm going to combine these two equations previously, and we're going to write down a schematical equation, meaning this isn't, you know, mathematically super precise. There's some terminology, but this is a good way to think about how the measurement actually works. So what we've got on top is omega A from here. And what omega A is it's some sort of measured quantity plus a bunch of corrections. And here's two of the corrections that we have to make. This is the electric field correction, CE. This is the pitch correction, CP. We have a couple others that I'll explain. I'll talk about all of these terms in detail. And then we have to measure a magnetic field. which is a field map. We have to know this field in space and time in the storage ring. It's a big task because it's a 50-meter storage ring. And we need to know where the muons are present in the ring. Also a big task, tracking muons while they evolve them. And again, we have some small corrections that we need to make at the end that I will discuss. So I'm just going to go over here to the storage ring quickly, so you can sort of see what the big players in this experiment are. So on the left here, you can see a top-down view, and on the right, you can see an actual picture. The beam is delivered through these magnets here and into the storage ring, where it begins to circulate in a clockwise direction. So the first thing that we have to do is we have to get the muons into the storage ring. And this is, of course, a problem because you can see the magnet here. This is a big magnet. It's a 1.45 Tesla field. And the muons start on the outside, but they need to get to the inside. And if we were to just fire them through a hole in the magnet, there's a large magnetic field in there, they would be deflected, hit the magnet, and be lost. So what we do is we actually have a hole bored through this magnet, and there is a secondary smaller magnet called the inflector magnet that lives inside of that hole that generates an equal but opposite field to the main magnet, canceling the field completely in this region where the muons penetrate the outer shell and get into the field, while simultaneously having as small as an edge effect as possible so it doesn't perturb our field in the actual storage region. It's a remarkable little bit of engineering, and that's right about here as it kicks us, as it gets into the ring. So I'm going to show on the top-down view here. The issue now is that the beam comes through the inflector with no field, so it's traveling straight, and then it comes into the ring. But because it came from the outside, it's not centered in the ring. It's actually living too far out radially here. And if we have a constant field, as we're going to undergo circular motion, it'd be too far out here, and on this side, it would be too far in. We're sort of, the circle is shifted upwards in this case. And so what we do is right about the cross point where the muons are circulating around, they actually do cross over their ideal orbit, set by the fact that we need this gamma factor to be precise to cancel the electric field that we have. So right where it crosses over we call it the magic radius, we have a set of 3 pulsed magnets, and it's just one, right when the muons go by the first time, they pulse and provide a brief magnetic field that kicks the muons onto their ideal orbit. These are the kicker magnets. And the muons only go through the kicker field a couple times while circulating. So now we need to provide focusing for the beam now that it's in here. Horizontal focusing, radial focusing is provided by the magnetic field. This is easy enough, but we need to provide vertical focusing. We can't do this with more magnetic fields because we need to make a precision magnetic field measurement here. This needs to be a very constant field. So instead we provide vertical focusing with electric quadrupoles, spaced sort of as you see around here. They provide a vertical focusing. They defocus a little bit horizontally, but that's countered by the magnetic field. So we have a nice contained beam. 24 calorimeters, you can see in this picture, that's these boxes positioned equally around the ring. This is where we collect our decay positrons for the actual omega A measurement, and I'll explain how that works in just a few minutes. And in 2 locations, right about here and right about here, before calorimeters, we have tracker systems, which can actually trace the decay positron's path and extrapolate back to the decay vertex, which we can use to determine the muon distribution in the ring without making a destructive measurement. And that's important. It means that in real time, while we are collecting omega A data, while we are collecting field data, we can also be collecting information about the muon distribution without influencing those other measurements. And so that's very important for us. Okay, so how do we actually use calorimeters to measure this frequency omega A? Well, we're helped out here a lot by parity violation. When you have a muon, and the muon's going to decay into a positron and 2 neutrinos. Because of parity violation, the decay positrons, the highest momentum decay positrons, which are, when decay positron goes in one direction and the neutrinos go out in the other, those are limited towards being emitted in the spin direction of the muon. So when we're in the lab frame with a boost in a certain direction, the highest energy positrons we observe are emitted when the spin is parallel to the momentum. So on the right here, you can see a distribution of how many positrons of a certain energy we see as a function of the energy of the positron. And what you can see is as we step through the spin and the momentum phasing and dephasing, when we have them in phase with each other, in line, parallel, we have an abundance of high energy positrons. When they're anti-parallel, we have fewer of them. And so what we can do is we can look at the counts of the positrons as a function of time of these highest energy positrons. We put an energy cut on them. And what you wind up with is a plot that looks like this. You can see that we're decreasing over time. This is just muon decay happening. But this wiggle that we see, this modulation, is our measurement of omega A. This is where most of our uncertainty comes from. We are statistics limited at 434 parts per billion compared to our total of 460, with systematics of only about 56. Okay, so we need to make some corrections. There's the electric field correction, which comes from this term in the anomalous precession frequency equation. We try to get this as close to zero as we can, but of course that's impossible. There is a momentum distribution of positrons, which means that there is a distribution of gamma ratios, gamma factors. Luckily, we can calculate the effect of this. It is related to the width of our beam in the x direction. Again, this is because the electric field causes radial defocusing. So we can use our trackers, and we can use the width of the beam to determine what the actual size of this term is. And we can calculate this and plug it in as a correction. This correction you can see is quite large. This is a 489 part per billion correction, but we know it quite well. We know it down to 53 parts per billion. So it's a large correction, but well known. There's this pitch correction. And this is related to the fact that the muons do not travel exactly orthogonally to the field. They swim up and down a little bit, caused by the vertical focusing caused by these quadrupoles. Once again, though, we can access this through tracker data because there's a relationship between how much are you actually swimming, what's the beta dot b from your vertical motion, and what the actual size, the extent of your vertical motion is. So you can look at the width, the vertical width of the beam, and access this term, and we can come up with a correction for this as well. Much smaller correction, 180 ppb, and better known, 13 parts per billion. Okay, now we get some fun corrections, and I say fun because, well, they sort of come in interesting ways. So, when we measure this wiggle plot, we're going to measure a frequency. We're going to do a fit. And we're going to fit something that's proportional to sine of omega A t. So we're just trying to pull out the frequency component of this sinusoid. Anything that creates a time-dependent phase, if there is a linear component to a time-dependent phase, that will be falsely interpreted as a shift to the frequency that we care about. In other words, if there's a first derivative to some sort of phase in that sinusoid, it is a false signal. So we have to think about, okay, well, where can we get sources of time-dependent phases? One of them is that there is a phase dependence between that depends on your momentum of your muons. And because we have muon losses, over time, our muon momentum spectrum changes. So there is a relationship between the phase and the muon distribution, and the muon distribution changes over time, which means that we have a phase over time change. So we need to measure both of these things, and we can use that to come up with a correction here. This is a very small correction. This is about 11 parts per billion, and it's even better known, down to 5. My sort of rule of thumb is if it's 10 parts per billion, we're in great shape. Okay, one more here. this is the phase acceptance correction. And again, it's a question of, is there something that correlates with phase that changes over time? And in this case, the decay position of your muons has a correlation with your phase. And in run 1, we had some damaged hardware, some damaged resistors that caused the beam to actually shift over the course of a fill. Essentially, one of the quadrupoles wasn't charging as fast as it should, which meant that there was an unbalanced electric field. And as it slowly charged, it moved the beam with it over the course of the fill. So again, we have a correlation with phase, and we have this correlation changing over time, which leads to a systematic effect. In this case, we see it's about 158 parts per billion with a 75 part per billion uncertainty. And this is one of our larger uncertainties. However, we are fairly confident that we can drive this down in further runs, and I'll explain how that works a little bit later. Okay, so I'm going to talk now a little bit about the magnetic field measurement. So the magnetic field measurement starts, it's basically one long calibration chain. We need to ask the question, what is the magnetic field that our protons would experience if they were in the exact same places as the muons at the exact same time? So we have to calibrate back to something that is a water probe. We do this at Argonne National Labs. We have a very well characterized water probe that we put into an MRI magnet to calibrate. We cross-checked this with helium-3 in what was, I believe, a first, using the helium-3 NMR instead. It's nice because it creates, there's a lot of different systematic effects between the water and the helium-3. So we then take this exact probe, the calibration probe, we transfer it from argon, and we actually put it on a lever arm that sticks into the magnetic field. And we use this to calibrate the trolley. And the trolley is a trolley. It lives on wheels, it lives on rails inside the vacuum chamber, and we literally drag it around, and it's got a suite of NMR probes in it that we use to measure the magnetic field at about 8,000 azimuthal locations every 3 days. So the plunging probe can actually be stuck into the exact same region of the magnet that the trolley probes live in, and we can sort of move them back and forth. We put the trolley in, we remove it, we put the plunging probe in, we remove it, put the trolley back in, and we can do this enough times, and we can transfer the calibration from the plunging probe, from the calibration probe, to the trolley. Then when the trolley drives around the ring, at 72 azimuthal locations, we have more NMR probes, a total of 378, that are not in the actual storage region. They're sort of at the top and bottom of it. Because they're not in the middle of the ring, they won't block muons. We can't have the trolley going while muons are there because it will block it. So we have these ones that are slightly further out, and we can transfer the calibration from the trolley to the fixed probes. The fixed probes are nice because they can measure even while the muons are present. So this is what gives us our time data. This is what gives us our spatial data. The way I like to think about it is that the trolley is sparse in time. We only run it every 3 days or so, but dense in space, 17 probes, exactly where the muons are. The muon distribution, I'll show you how it looks relative to this in just a moment. However, the fixed probes are sparse in space. We only, they don't live exactly in the right spot, and we only have 72 azimuthal locations, but they're dense in time because we can measure about every 1.5 seconds out of all of them whenever the muons are present. Okay, so we get some field maps from the trolley, and as I said, the trolley just drives through. We pull it around with a fishing cable, and about every half a second as we're pulling it around, it takes a field map with those 17 NMR probes. These are nice. This is our best determination of the magnetic field. This is how we know what our baseline field is. And we can do this quite well. We can get this to about 25 parts per billion. But then we have to pull the trolley out of the ring. It's got a little garage. It's very cute. And then we have to ask, okay, well, what's happening between the trolley runs? And this is where the fixed probes come in. So we have to synchronize the fixed probes to the trolley during the trolley runs. And then they track between the trolley runs. They give us additional points for interpolation. So we track very well. You can see on this plot, the blue lines are what the fixed probes see. The orange line is what the trolley would see. This is in what we would call a stationary run, where we park the trolley for 3 days and just let it evolve and see how the fixed probes and the trolleys react. With this, we can see very well what's that the trolley tracks the fixed probes quite precisely. So I mentioned that there's a couple little corrections that we have to make for the field. These are both fast transients. These are fields that are created by some other effect in the ring that are too fast for NMR probes to see. The NMR probes can only measure about once every second. So anything that's significantly faster than that, they are sort of insensitive to. So the big one for us is these electric quadrupoles. When you charge them, they begin to vibrate. They are now a charged object vibrating in a magnetic field. They generate eddy currents that perturb the field while the muons are present in a correlated way with muon injections. So we had to make special probes to measure the size of this perturbation. I'm going to zoom in here so you can sort of see what we're looking at. The gray band here is the time the muons are present. The blue line is the perturbation caused by this eddy current. And you can see we have to sort of measure, okay, well, how much of a difference does this make over the course of a fill? And then we have to average that over all of our fills because we get 16 fills sort of per cycle. This is our largest source of uncertainty besides the statistical. This is our largest systematic uncertainty at 92 parts per billion. Again, we think we're going to be able to drive this down just through further data taking, especially this summer. You get a similar sort of effect from these kickers. When the kickers fire, we're not taking data. That's a vetoed period. So it doesn't matter that they have a large perturbation in the field. However, even after they're done firing, there's an eddy current. There's a sort of a decaying transient that we have to account for. So we have a special optical Faraday magnetometer. This is a very fast kick, and we've measured the size of this transient so that we can make the correction in the field. 5. Okay. This is about a 40 part per billion uncertainty for us. Okay. I mentioned these straw trackers, which track the muon distribution in the ring. We have to use this to weight the actual average field the muons will see. What you can see here is the muon distribution in color overlaid over our magnetic field map. So you can see how we're going to sort of use this field to weight and average the magnetic. Sorry, we use this distribution to weight and average the magnetic field. So using these trackers, we can sort of figure out where in this vacuum chamber these distributions live. The trackers are very cool. They're actually these layers that can detect positrons passing through them. And what you can do is every time you get a hit, you can connect hits from one positron and extrapolate it backwards through your magnetic field and figure out where did it decay. And we can take these decay vertices and turn them into a muon distribution that we can use. Okay, so I'm going to just go over here the uncertainties very quickly, just sort of as a reminder. First takeaway, we are dominated by statistics, 434 parts per billion out of 460 total. Our largest systematic uncertainties are this phase acceptance term and this quadrupole transient. Both of these, we believe, are better in our next measurements. This because we will have more data. This is the uncertainty here is driven by the fact that we don't have a great map of the spatial dependence of this transient. So we'll get a better spatial dependence of the transient and drive down this uncertainty. The resistors have been fixed, so this uncertainty should just be driven down naturally by the fact that the experiment is working better. So I'm going to go back over the results just a moment again, just refresh this in your mind. We are statistics dominated, as I mentioned. So was Brookhaven. So it is natural. It is reasonable for us to combine these into a new world average. We have about in run 1 about the same number of statistics as BNL did. We are about 4.2 sigma from the standard model at the moment. And you think, okay, well, what can you do? It's 4.2 sigma, it's not 5. Well, what's coming next from us? This I've shown you is only our data from run 1. We have already collected 4 times as much data in runs 2 and 3, which are currently being processed with hopes to publish, in about the year scale. Run 4 is currently underway. This is a little bit of an older plot, so we're actually significantly higher at this point. And we're bringing down our systematic uncertainties through a combination of our upgrades and systematic studies, as I mentioned. So we're driving down statistics with more data that we already have. We're driving down systematic uncertainties. And so the future is very exciting to see where we land. And I want to thank some people. You can read who I want to thank. And thank you very much.
Thank you very much, Alec, for being so well on time and for this excellent talk. It's time for questions. Please raise your hand. Okay, I don't see any question. Right.
I'll ask a question.
Please, go ahead.
Yeah, this was really nice talk, Alec. Thank you very much.
Thank you.
Yeah, you talked about, I mean, I don't think you discussed about your calorimeter, because it's such a basic element for your counting. Well, maybe I just not familiar.
Right. So the calorimeters are what we use when we have to sort of measure the energy of the decay positrons. So what we're doing with the calorimeters is we're actually just sort of binning high energy positrons as a function of decay time after injection. So the calorimeters, if you take these bins, this is sort of the output of the calorimeter, is this wiggle plot.
Yes.
So this is this is where the actual omega A measurement comes from. It's just you can actually, it's really interesting. You can almost take this straight from the calorimeter data. In fact, we have 4 different methods for extracting omega A from the calorimeter data that have to do with how you're dealing with these cuts and with other things that can cross-check each other. One of these methods actually just pulls bins directly from the calorimeter and uses that as the data without making any sort of these sort of don't want to get too far into that, without making any sort of big data sweeping data cuts on it. So you can almost directly take the raw data and see the omega A in it. It's very cool.
So there's no time dependent issues or considerations on the calorimeter side? Oh,
there definitely are. You know, we have one of our biggest issues, leading cause of systematics, is pile-up effects, where you wind up with positrons, you know, multiple incident positrons depositing higher energy than they should have, or any individual one would have, that you have to deal with. I did sort of gloss over that. There's the actual analysis that has to go for omega A is very deep and involved, and deserves an hour-long talk all of its own.
Mm-hmm. Thanks.
Mm-hmm.
Very good. Any other questions? I have a couple myself, if I don't see any. Okay, so one is, may it be possible that you end up acquiring more data than initially planned? And my other question is, may also be possible that you acquire data with muons?
Sorry, what was your first question again?
You have some plans for the data that you could accumulate after all runs, but maybe you can continue after that. Is that possible or not?
This is, it depends on scheduling. We share the muon campus with another experiment that's about to turn on, mu to E. So they're going to come online soon, and we're going to have to share beam time with them. And there's also funding considerations. But we do have hopes to extend our run. I believe we are currently thinking there's a run 5, and there's a possible run 6. And there are discussions about whether to flip the field and run 6 with muons instead of anti-muons. But this is all sort of speculative at this point, because we need to see how scheduling plays out.
Thank you very much.
Pablo, I'm not sure if you're able to see the raised hands. Can you see them? Because I see 3 right now.
No, I didn't see it. Thank you for telling me. So who has?
And there was one from Chiking as well before.
Go ahead, please, Chiking. I'm sorry.
Well, I see the other raised hand probably, so that I'll let them ask first. My question is not so important, so I can skip it.
As you please, I think it was Genaro, maybe. Is it possible?
Now there's Wolfgang at the top.
Yes. My question is very simple. In your formula, it seems like the electric and magnetic field appear as classical fields. So does it make any difference if you treat everything consistently with QED?
Right. So this is always sort of a sticky point when you're looking at sort of the actual QED here. We do have to insert a classical field. We have to couple to a classical field out here. So it is treated in a fully QED fashion. However, you know, we do have a classical input to it. I don't know if there is a proper way to quantize a classical field. I can barely do this with a classical field myself. But yes, it is we do, I guess the best answer I can give is we do couple a classical field in the equations, but I'm not sure if that is a source of problems or whether that is for some reason okay. Sorry, I can't answer that any better.
Thank you very much again, Alec, and I think we need to move on. So thank you a lot again. There will be time for discussions later on in the Eureka rooms. So now we will have the pleasure of listening to Professor Siking Zhang. He's been leading worldwide the effort for computing this in the standard model. So we are eager to listen to him. Can you please start sharing your slides?
Yes, I'm trying to find my screen. Somehow I don't find
the green button.
Yeah, somehow I don't find the right one. I have quite some screen there. Let's see. Okay, maybe I'm doing this way. I just show my screen so that that should be fine, I think. Okay, can you still see it?
Yes, fine. Thank you.
Good. Thanks for the invitation. It's my pleasure to give this talk here, and I'd like to give a nice introduction, so I could skip some of my slides since I have many slides. Good. So basically, yeah, this is explained. The thing I want to point out is that yeah, we can, as Alex showed, we can measure this quantity very precisely. And then on the series side, we could also measure, predict with comparable precision. So the comparison of the two, if there was any discrepancy, could be a sign of the new physics. So that's why it's very exciting. And this is not the only quantity that we could measure and predict precisely. Actually, in fact, the AE, the version of electron, is even more measured or predicted in better precision. But given the fact that muon is 200 times heavier, so in terms of the sensitivity to new physics, actually muon is well placed compared to the electron. So that's why muon is more exciting to probe and to measure. And as Alex mentioned, there is a long history, actually more than 60 years measurement. And there is also a strong interplay between the measurement and the prediction. So at the beginning with the limited precision, we start already to probe the QED contributions, the first low order QED contributions. And as the measurement became more precise, we are probing and higher order in QED. at some stage we are becoming sensitive to the hadronic contribution and weak contribution. And now, since we see some differences, it could be physics beyond the stand model. Right, so this is different versions that Alex showed. Currently in the white paper, this theoretical prediction is a merging of the two group. Prediction from two group. One is from our group. I will give some new details on this, and another one is from another group. Basically, we are using similar data, but we have somehow different philosophy in treating the uncertainty. In our case, as I mentioned, I will tell you later why our uncertainty is larger. So we are somewhat conservative. And the white paper actually followed our approach. And so that's why also the white paper uncertainty is similar to ours. Nevertheless, you see that we have this discrepancy there. At some stage, I will mention this, the prediction from lattice side, although it was not used currently in the prediction, but once this result prediction is confirmed or the precision is improved, then either we have a discrepancy then we need to understand, or we will see when this situation becomes clear. Okay, now I talk about a bit on the different contribution from theory side. So in principle, you could have both contribution from standard model, all the sector, QED, strong interaction and weak contributions. And then you could have a contribution beyond standard model. So for the QED, this is the lowest order. This is G factor equal 2, and then this is Schwinger first order contribution that Alex mentioned. And then you have high order contribution as well. And on the strong sector, you have this leading order vacuum polarization contribution, and so you have the light by light contribution. And weak sector, you have different bosons contributing. And then we could have SUSY or something else contributing to different high order. Now, so just on one page to see the relative contribution from different sectors. QED, of course, is the largest contribution, although the precision is very good, right? And weak contribution is much smaller, and also the precision is good. And then the hadronic contribution is larger than the weak one, but much smaller than QED. But it has a dominant uncertainty. That's why the focus, most of the work actually is going to this component. There was another contribution from hadronic side. This is light by light contribution. It has the second largest uncertainty. So there, eventually, we also need to improve the precision. Okay, then on the QED side, actually we have, this is known to fifth order. And you see in terms of the alpha, you see that this is converging very nicely, that now each term becomes smaller. And basically, I think, this is, except probably the last two terms, they are not fully cross-checked, but most of them are known either analytically or cross-checked with other different means or methods. And the uncertainty, although small, is dominated by the high order estimation. Now, next, the weak contribution. you have a few example graphs here, the loop, one loop contributions and the two loop. There are more, of course. Here are a few examples. The leading first order loop is the dominant one. Then you have also other different components from in second order loop. And the high order is negligibly small. Now, let's concentrate on the leading, the hadronic contribution. It has actually several components: the leading order, the high order, and the light by light contribution. So I will concentrate on the leading order prediction, and later I will flash the prediction for the other two terms. So as Alex mentioned, this cannot be done from first principle because it's at a low energy scales that the perturbative theory don't work. So we need to find other means. Over the years, this is done by so-called dispersion relation, namely that you can connect to this leading order contribution with the E plus minus annihilation to hadron cross sections. And so using this formula where you have this K, this is the QED kernel, and you have this energy dependence such that the low energy data has the largest contribution. And actually the dominant channel is the 2-pound channel, which gives over 70% of the contribution to the leading order part. It's also dominant in terms of the uncertainty. Right. So now let's talk a bit about the measurement from different experiments. So we have basically two types of measurements. One is so-called the scan method. So you have the E plus minus machine, and the beam energy is fixed. Yeah, you measure different final states. Then you have another type. This is so-called ISR, initial state radiation approach. This is, for instance, the method used by the Barbour and the Chloe experiment, where you use the fact that there is one initial state radiation from one of the beam, such that the effective center of mass energy depends how large the radiated photon is. So then you see that for the first method, for each, you need to fix the beam energy and measure at that energy, the cross section. While the other method, basically you have a continuous measurement of energy depending the photon energy. So yeah, it's good that we have this different methods, so they have different systematics, and so that could be interesting to compare. And they also have different energy coverage and different statistical systematic uncertainty. Okay, so this is a list of the channels that we studied in our latest publication. So below 1.8 GeV, where the contribution is the largest, we have something 30 exclusive channel evaluated. In fact, our group has been involved in this since more than 20 years. And the previous prediction was used for comparing to Brookhaven experiment, where giving a deficit about between 2 and 3 sigma. But that gives us motivation to continue this effort for more precise predictions. So in the following, I will give a few examples of the measurement from different experiments in the dominant channels. And then I will discuss the combination of different measurements for given channel and talk about the comparison, the tension between different measurements. Okay, so yeah, starting with 2-pion channel, these are two measurements from CMD2, yes, more than 10 years ago. Well, their latest measurement is still, well, hopefully will be published soon with improved precision. So they have typically, you see, we covered this energy range between 350 MeV up to 1 GeV with various precisions. You see the energy density, well, points depends where to choose a beam, right? So in the low resonance or this interference low omega region, they have more data points, but in the off the peak, they have only a few measurements there. The typical systematic precision is between 0.7 and 0.88%. The SMD measurement about the same time have somewhat larger systematic uncertainties. Since they are sitting in the same machine, so they actually, the energy coverage are basically the same. And then there was a new measurement published recently, which gives improved precision. But this measurement is not included in the white paper since it came after the publication of the white paper. Then another example is the Chloe. They had actually two data sets. One is around 208, whereas the photon is at small angle, undetected. And they measured actually with respect to using a called a radiate function from QED actually. But later they reanalyzed this data. This time we measure the cross-section 2-pion over the mu point-like process. And so some of the systematic uncertainty canceled. Then they have another measurement about 10 years ago using the large angle photon. Well, their beam energy, you see, is only slightly above this measurement energy region. So that's why actually their photon is really soft. So in order to measure larger angle, so then you need to actually, well, this in fact helps them to access this low energy region, which is more interesting in terms of the HVP contribution, because their contribution is the largest. On the other hand, for the Baba, and they actually, well, the beam energy is a factor of 10 or 1 order of magnitude higher. So there, the radiated photon is very hard, and so they are measured at essentially detect a large angle. And this also allows them to cover a very broad energy range from threshold up to 3 GeV. And they measure the cross-section over the mu. And so as I mentioned, some of the systematic cancers. And this is, for instance, the 0E data over the QED prediction. You see it's very flat. And then two more examples from BESS3 and Chloe E. They use also the ISR method. So the precision here is comparable, 0.9% on one hand, and 1.5% systematic for the edge experiment. Okay, so then in terms of the leading order HVP contributions. So this is a comparison between these experiments in their common energy range between 0.6 and 0.9 GeV. Then you see that, yeah, first of all, the precision not the same. The two most precise measurements are Chloe and Baba, but there's a large discrepancy beyond the quoted systematic error. So this would be one of the main issues when combining these data, that we need a special treatment, as I will come to this later. So then over the years, we have developed a tool, what we call the HVP tool, which first of all includes all the data set measurement I mentioned, not only for two-parent channel, but for all the other decay channels. And then basically it combines experimental spectrum with arbitrary spacing and binning. You see that for a given experiment, the energy density is varying from one energy region to another. And to predict the HVP, and then you need to interpolate between different energies, data points, measurements. So this is how we handled this. And then, of course, we need to treat the correlation for a given channel or yeah, between different beams or data points, or between different channels. So we use kind of pseudo experiment to do this. And then finally, the combined result could be shown in very fine binning, finer than the initial, for instance, measurement binning. Okay, so this is the outcome of the combination showing in this green band, and then compared with the individual measurement. This is for the dominant two-pound decay mode. So you have this rich spectrum, the resonance, low resonance, the low omega interface, and then the other high mass resonances. And here's a zoom into different energy range, so that one can see better how, yeah, the different density or the precision of different experiments, yeah, in comparison with the combinations. And this is another way showing the difference between different experiments. For instance, Baba has a tendency to be above the combination. On the other hand, Chloe's are basically systematically lower than the combination, and the other experiments less precise, they are basically in agreement with combinations. Right, so another way to see the relative weight or contribution in the combination of the different experiments. This is the relative weight from different experiments. So you see that all over the large mass range, Baba essentially dominates over a large range. Only in this Rome resonance region that Chloe sometimes has a larger weight. This plot shows the tension, between different measurements. This is basically the local the chi-square value over the number of degree of freedom. Yeah. So you see that, well, ideally you want to have this at 1, right? So that all the measurement would be consistent. But occasionally you see that at some of the points, there is a large scale factor. And this, we take this into account locally in our combination. And this downgrade, of course, the precision in the leading order predictions by 15%. Okay, I will spend a little time talking about one phenomenological fit we did in our last publication at low energy. Basically, that, well, I apologize for this so many formula, but the idea is very simple. Namely, you extract from the cross-section the form factor, and then you parameterize this form factor with two functions with different consideration. For instance, in the G, this raw omega interference contribution is shown in this term. And so, yeah, basically we have 6 free parameters listed here to fit using all the data from two pion channels. Then we can see how this agrees with this phenomenological models. For instance, here the blue band shows the fitted result with the corresponding uncertainty compared to the Baba and the Chloe again the other experiments. And then you also see 2 lines. For instance, this red line shows when you remove the Chloe experiment from the combination, then you would have such a fit. Basically, the agreement with the Baba, and then as the way around, if you would remove Baba and do the fit, then the curve becomes lower than the other one. So you see, so this is summarized here. The green band is the direct data combination, and the blue band is a fit, a phenomenological fit to all the data, and this is 2 curves that I just mentioned. So clearly you see that there is a tension, right? So because of the Chloe and the Baba discrepancy. So this needs to be taken into account in all predictions. Now, in terms of the precision, you see, either using directly data for the integration, we get such a result. In terms of fit, we see that we basically improve slightly the precision. The central value stays consistent. Okay, now we need to combine our low energy fit with the data integration at high energy. And this is the result we get. If we take all the data, we get such uncertain 1.9 in total unit. And if we take out all the data without Baba, we get this, and the other way around without Chloe, we get another prediction. So you see that the difference of 5.6 unit is much larger than the uncertainty one gets. So one certainly cannot live with this prediction. Otherwise, this is the uncertainty is underestimated. So the approach we did, this makes the difference with the other group, is that we take half the difference as our additional uncertainty, and we take the average mean as our central value. Okay, so I talked about the 2 pion channel, but there are many other channels in total below 1.68 GeV. We have about 40 process, and this is an example of all the measurement performed by Baba experiment. You see for the pi or different pi modes, K modes, and other modes. They are contributing to different energy range. And so I talked about the tension in 2-pion. This is not the only place we have tension in the other channel. I gave another example, the K plus K minus channel, for instance. We have this 5 resonance here. And so you see here, for instance, even the CMD and CMD3, 2 and 3, is the same experiment at different time. You see that they don't agree, within the uncertainty quoted. So then in the combination, we have to take into account this tension into account. Although this channel only contributes to 2.3% to the total contribution. Okay, so a big picture, putting everything together. Combining all the exclusive channel below 1.8 GeV. So we have roughly around 30 channels I mentioned. And so this is the R ratio, the dependence as function of energy from threshold up to 5 GeV. And then you also see different resonances. And this energy range of where we made a special comparison between perturbative QCD prediction and the data directly. We tested in particular this range, energy range between 1.8 and 2 GeV. Between the exclusive sum and the perturbative predictions. We take the difference as the sort of duality uncertainty in our estimation, showing next page. At a high energy, we take a perturbative prediction, which is pretty reliable. We have tested this. So this is the overall result for all these channels that I mentioned, both for the mu G-2 and for the strong the fine coupling at the Z mass. And then you have different resonance and also perturbative contributions at high energies. In total, this is the result we get.
5 minutes, please.
Yeah, okay. So basically, I think I can skip some of this. Well, I can quickly go through this. A few years ago, we were actually using another method to do this, namely relying the isospin symmetry and make the connection, the E annihilation and the tau decays. At that time, the tau data were still precise or as precise or even slightly more precise than the E plus minus data. And but the situation has evolved. One complication is that we have to take into account the different isospin breaking effect into account. And in this publication, Gabriel was one of our collaborators. And so he's an expert on some of these isospin corrections. And we made the comparison with another group, and we found a good agreement from most of them, but we also see a slight difference in some of them. One particular difference is this so-called row gamma mixing that I will come to this shortly. So this is a comparison for 2-pion channel between the tau average data and E plus minus average data. So you see the different shapes. To some extent, this is driven by the Chloe data. And another way to compare this is to derive the equivalent, the branching ratio or fraction from the E plus minus data, compared to the direct measurement from tau data. So you see there's some kind of discrepancy there. Although the Barber measurement is in agreement with the tau data. Yeah, so the other group proposing this row omega mixing as additional correction, and we tried this. In fact, it does not seem to work. You see, once apply this correction, the compressor becomes worse in some of the regions. So okay, so you see, we have this open issue of isospin correction. And then also nowadays, the E plus minus data are more precise. So that's why I no longer continue to do the prediction using the tau data. But the situation may change if we have more precise tau data, or if we have a better understanding of the isospin breaking corrections. Yeah, I should mention this as a channel 2Pi. You also see similar comparison there. One slide on the other prediction lattice QCD based one. So this is the red points shows the dispersion relation based predictions with very precise uncertainty or good uncertainty. And this is a lattice prediction, current lattice based prediction. You see there about precision. For the moment, it's very limited. That's why actually they were not included in the white paper, except that recently there was this BMW group. They have provided a precision which is comparable, or slightly larger, but comparable to the dispersive prediction. But you see, between their initial version and the final published version, there is already 1 sigma shift. And yeah, this prediction also is systematic dominated. So for the moment, yeah, we don't have a clear conclusion. Certainly, this prediction needs to be confirmed by all the other lattice group with comparable precision. Yeah, before we can draw a firm conclusion. Okay, one slide on the high order contribution, although they are small. So light by to light one, as I mentioned, is not the uncertainty is the second leading one. This should be also followed up eventually. So finally, summary and perspective. So currently the precision of the dispersive prediction matches with that of direct measurement, but the situation will soon improve or change with respect to the measurement side, because as Alex mentioned, that we expect up to factor 4 improvement in the next years on the measurement side. On the theory side, the situation is less clear. We do expect more measurements, for instance, the dominant 2-pion channel from different experiments. But given the discrepancy we have now between Baba and Chloe, we need a very precise measurement in order to resolve this discrepancy. Otherwise, even when we will combine them together, this won't help, right? And then we have this issue of lattice prediction. For the moment, they do not agree with this dispersive prediction. So if this is confirmed, then we have additional things to understand. Okay, thank you.
Thank you very much again for this very interesting talk. It's time for questions. Please go ahead. Gabriel, please.
Okay, thank you, Shikin, for this nice talk. Can you hear me? Yes.
Yes.
Okay. In your slide 27 or 11, can you show it again, please? No, next one, please.
Next one, this one.
No, the one where appeared the list of all channels contributing to.
You mean this one?
This one, yes.
Okay.
Here I can see several channels where you include resonances like eta omega, eta 5, omega kk, and other channels.
Mhm.
So strictly speaking, resonances are not stable particles.
Yeah.
And should not be included in the unitarity relation in the dispersive approach. And on the other hand, it seems to me that it is not clear how resonances and non-resonant contributions can be separated from a measurement. So why they should be included is one question, and the other one is if the two groups that get dispersive results include resonances.
Yeah, yes, okay, a good question. But you see, indeed, they may have some mismatch between the way we grouped here or with the measurement, because somehow actually in terms of measurement, we have more channels. Yeah, I mentioned at some stage we have 4D process, for instance, but some of them we somehow regrouped them together. So yeah, this is for simplification. Otherwise we have more channel to include. I don't know if I've answered your question. But yeah, one point I also should mention is that some of them we listed it because we don't have the direct measurement, so we need to use this isospin constraint to recover them. Previously, this actually correspond to a few % of missing channel, but the latest with all the measurement we have now, this become negligible.
Okay. So my question is because eta omega, for example, should be a part of eta pi channel, and you must make an assumption to separate in the cross section the two contributions, the resonant and the non-resonant one.
Yeah. Yes.
Okay. Thank you.
Any other question? I don't see.
I have one question.
Yes, please go ahead.
Hi, thanks for the nice talk. So this, possibly I didn't understand very well, but this discrepancy between Bauer and Chloe.
Yeah.
So it seems to me, do you basically don't use the data where the tension is highest, basically, between the two? Is that correct? But one could argue that, you know, this is very arbitrary. You know, one could argue that you should take both results as they are and just the weighted contribution. But why is it?
No, we do actually. You see, the green band is when we take both of them, right? This is when we combine everything together with the treatment, also with this local error inflation I mentioned. Then you see, once we have where it is, yeah, you see, when we have this local tension, we scare the uncertainty, the combined uncertainty by this factor, right? Depending the tension, but this is not sufficient. This is already taken into account the error band.
Oh, okay.
Error band.
I see.
But this is not sufficient to cover the difference between the two measurements. That's why we have additional uncertainty coded.
So you basically blow up this uncertainty.
Exactly.
To cover. Okay.
Yeah.
And just one quick question finally. Some of these results, surely Bell, the Bell experiment should have some results on this, and I don't see them included here, right? Is there a reason for that, or basically they don't exist from Bell?
Ben, I think it was including the tau measurement side. But
Okay.
for the E plus minus, I think it's not yet published. Well, if I'm not wrong. But
Okay,
yeah, as soon as they are measurement, of course, we will take that, include them, yes. But in the, well, I didn't give the detail there, but in this combination of the tau data, Barry was included.
Oh, okay.
Yeah.
Thank you.
Oh, by the way, you see it from here. All right.
They didn't. We hope for Bell too. Okay, so
Yeah. Yes.
it's time to close this session, but before, let us thank a lot Seeking again for the excellent talk and discussion. Thank you.
Thank you.
So, Jose, when do we reconvene?
Right, so we have now a break, and there will be time for more questions on the break.
And then what time do we reconvene?
Let's see, so we should be at the 10:27. We were supposed to start, we'll have 20 minutes. Well, let's try to restart at the scheduled time, which is 10:40.
Okay, 10:40, everyone.
Okay, bye-bye.
Bye, Shikin. Thank you for your talk.
Welcome. I'll talk to you later.
Yes, see you.
Alex, are you around?
Yes.
Okay. I don't know if you can start trying to share just to see if everything works.
Sí, Jesús, si puedes mandar un mensaje que ya se van a cerrar los cuartos.
Sí, doctor.
Gracias. So can we start, Jose?
No sé si ya se cerraron. A ver, espérame unos...
You tell me, you tell me.
faltan 50 segundos, creo, todavía. Ok, creo que ya.
Okay, so welcome back, everybody. We will start this session with Alex Miranda, who will be telling us about the computation of the big contribution discussed previously by King, but using tau data. Please, Alex, whenever you want.
Okay. Thank you, Pablo, and thank you to the organizer for this opportunity. And I'm going to talk about this new tau-based evaluation of the hadronic contribution to the vacuum polarization of the muon anomalous magnetic moment. And this talk is based on a published work with Pablo. Okay, these are the contents of this talk, and let's start. Okay, as a reminder, the G factor is defined according to this relation, and it was predicted to be 2 according to the Dirac equation. But now we know that there is not exact, and this is because some quantum effects. And the first correction was given by Julian Schwinger in 1937. And that prediction was confirmed by the Kush and Foley experiments. Okay, I'm going to skip this. And okay, in this plot, we can see the historical evolution on the theoretical prediction and the experimental measurement. And now we have a discrepancy of about 4.2 sigma. Okay, in the standard model, the anomalous magnetic moment of the muon receives 3 contributions, one from QED, another from weak interaction, and another from strong interaction. The QED part is the most important and has been calculated up to 5 order. And the weak interaction, the weak contribution has been estimated up to 2 loops. And the hadronic contribution are the most difficult to estimate. Okay, and the uncertainty is dominated by the hadronic vacuum polarization, followed by the hadronic light-by-light scattering. Okay, we can estimate the hadronic vacuum polarization contribution using dispersion relation, which complies with analyticity and unitarity. For the hadronic vacuum polarization at leading order, we have this equation, where this Ks is a kernel function that goes as 1/s at low energy. So this factor increase the contribution at low energies. And this term is known as the R ratio, where this is the part E plus and minus into hadrons cross-section. And it is possible to evaluate these contributions using the measurements of the cross-section of E plus and minus into hadrons, or using the tau decays, which can be related to the isobector component of the E plus and minus into hadron cross-section through isospin symmetry. And since both are subject to theoretical uncertainties, it is a good strategy to keep using both. Okay, about 73% of the contributions to HVP and 58% of the total uncertainty corresponds to the DPyC channel at low energies. And for the 2-pion final state, we have this relation. But when we include the isospin breaking corrections at leading order, we have this relation where this is the tau decay width, and this is the short distance electrowidth correction. And this function includes the corrections due to final state radiation, the GEM function that receives contribution from real and virtual photons. And this is a phase space factor, and this is the ratio of the electromagnetic form factor over the vector form factor. Okay, here are some remarks. It is well known that there is a discrepancy between the contributions to this part when we use E plus and minus or tau decays. And according to this work by Chirigliano, this could be a new physics effect. And in this work, we perform a global fit using hadronic tau decays to set bounds on new physics effective couplings. And in this work, we study a new physics effect in these decays using an effective field theory framework. And although the determination to the HVP at leading order using lattice QCD are still not competitive, with respect to the E plus and minus base evaluation, there is one lattice calculation by the BMW collaboration with an error of 55 times 10 to minus 11, in which there is no need to invoke new physics to explain the discrepancy. But we need to wait for another lattice group to confirm or refute the results. And also, there is a solution for this problem given by Jäger-Renner and Safron that induce an additional correction due to the rho gamma mixing in which the rho is regarded as a gauge boson. Okay, the radiative decays are very important, so we need to keep under control these decays. For this decay, the matrix element is given by this equation, where this term B8 corresponds to the vector and axial form factors. And that term can be split into two parts, a structure independent and a structure dependent part. Okay, we use chiral perturbation theory, which is an effective field theory that describes the standard model at low energy. And okay, there is a difference for the effects of the structure-dependent part when they are evaluated using KPT with resonance and the BMD model. The last one is a work by a Mexican group. Okay, at order P to the 4th in KPT with resonance, we have the following contribution. On the left, the contributions to the vector form factor, and on the right, the contributions to the axial form factor. Okay, in this work, we extend the previous calculation made by Chirigliano at the next to leading order using the operators given in these two papers. And we found the following contribution, where we have now diagrams that include an omega exchange. Okay, but now we have too many parameters allowed by the discrete symmetries of QCD and chiral symmetry that prevent us from making phenomenological prediction. But it is possible to reduce the number of couplings using the short distance properties of QCD, and so and to estimate the remaining parameters, we relied on chiral counting and an estimation of the legs of the order P to the 6 KPT Lagrangian. And the kappa B couplings, which are related to the omega exchange, contribute significantly to the radiative decays. We perform a global fit using the relation for the resonance saturation of the anomalous sector. Okay, and here are our prediction for the decay spectrum of the radiative decay. And this is the result for the different orders of approximation. And in the blue region, we have the full order P to the 6 contribution. Okay, we have a huge region, but this is because we don't know the many couplings. So any measurement on these observables will allow us to reduce or to set bounds on these couplings and thus reduce the errors. And this is the prediction for the branching ratio. Okay, now we can put all these contributions together, the virtual and the real photons, and we get the GEM function, which is defined according to this relation. On the left, we have the results using a dispersive parametrization of the vector form factor. And on the right, we have the results using the exponential parametrization used by Chirigliano. Okay, now we can estimate the effect of each isospin breaking correction through this function, which measures the deviation with respect to the isospin limit. On the left, we have the results at order P to the 4, and on the right, we have the results at order P to the 6. Okay, here we can see that we have a larger uncertainty. Okay, an important cross-check that we can make is to estimate the branching ratio using the E plus E minus data and compare with the measurement. Okay, using the Babar data, we get 24.68% at order P to the 4 and 24.17% at order P to the 6. And these two results are in good agreement with the value reported by the Bell collaboration. Okay, another important cross-check that we can make is to compare the prediction for the cross-section using tau data and compare with the E plus E minus data. Okay, and since it is known that there is a discrepancy between the two most precise measurements from Babar and Clow, we put this in these plots. Okay, above we have the Babar data, below the Clow data. And as we can see, our results improve the agreement with respect to the Babar data. And also we can change the raw decay width, and the effect of that is to improve the agreement in the raw region, as we can see more clearly here. Okay, and now using all these results, we get the contributions for this channel to the hadronic vacuum polarization at this order P to the 4 and order P to the 6. And now if we include all the other channels and contributions, we find the overall HPP contribution at this order P to the 4 and order P to the 6. Okay, and finally, when we include all the other contributions from QED, electroweak, and subleaded hadronic, we find that the 4.2 sigma deficit is reduced to 2.1 sigma at order P to the 4 and 2.3 sigma at order P to the 6. And in this plot, we can see where are our results. And as we can see, when we include the higher order contributions, the value is shifted toward the E plus E minus estimation. And finally, the conclusion. There is a global effort in improving the hadronic contributions to AMU, specifically dedicated studies to improve the HPP part from lattice, dispersion relations, and improve E plus E minus data, and Monte Carlos are being undertaken. And the observables for the radiative decays have the potential to reduce drastically the errors in our estimation. Our isospin breaking corrections improve the agreement between E plus E minus and tau data on the spectrum and the branching ratio. And evaluating the HPP leading order contributions from tau data, we get these two results that reduce the anomaly to 2.1 sigma and 2.3 sigma. And okay, here are some reference, and that's it.
Thank you very much, Alex. Very well and even on time. So, questions for Alex? I see Johan and Wolfgang. I don't know who was first.
I can wait.
Okay, Johan, please, and then Wolfgang.
Thanks. Jesus, thanks for the well talk. I have a question about the, I don't know what is the reason about the reason why the uncertainties is major in your studies for the order to B26. This uncertainty is greater than the order to B to the 4. What is the reason? I don't know.
Mm-hmm.
Thanks.
Okay. Okay, as I told, we have now a lot of parameters, and we can estimate some of them, but this is not enough to get a precise prediction. Here, for example, we can see that the effect of this contribution is large, but if we can measure these decays, we can set bounds on these couplings, and so the prediction will have a laser uncertainty.
Okay, thank you. Can we have your questions, Wolfgang, in the breakout rooms later on?
Well, I would regret, but okay.
Okay, please.
Yeah, it's a short question. It's about this remark about the solution by Jägerleiner and the collaborator who assume a rho gamma mixing, and you say he deals with rho as a gauge boson. Can this be justified?
No. It's a model dependent assumption.
Okay, thank you.
Okay, thank you again, Alex. So now we move to our next speaker, who is Kepani Raya from ACN UNAM and Nankay University, who will be speaking about Dyson-Swinger equations and the mu and G-2. Please, Kepani, can you start sharing your slides?
Thank you, Pablo. Can you hear me?
Yes, very well.
Just one note,
Okay.
Pablo, just to note that there will not be another coffee break. So all the questions should be asked, I think, after each talk.
Thank you, Jose. I'm sorry.
Okay.
Please, Kepan.
Thank you. So as Pablo mentioned, I will talk about Dyson-Swinger equations and the mu and J-2. This is a work in collaboration with Adnan, Angela, and Pablo, of course. And as all of you know, this observable, the muon's anomalous magnetic moment, is a well-known observable that has been studied for a long time. So some decades ago, we were in the CERN era, followed by the Brookhaven era, which triggered both experimentalists and theorists. And now we are entering the Fermilab era, which actually, as you may know, Fermilab kind of confirmed the early findings by Brookhaven. So this historic discrepancy remains. So this observable EMU is an ideal platform to ask many questions and try to improve from both fronts, experiment and theory. The beautiful thing of this observable is that all particle physics is there. And from the standard model point of view, we can split it in many parts. The QED part, the electromagnetic part, which is dominant and very well understood. The electroweak part, which is also under control, and the hadronic part. The hadronic part dominates the uncertainty, I will say because of the non-perturbative nature of QCD, that it is hard to tame. We can divide this hadronic part in two contributions, the hadronic vacuum polarization and the hadronic light by light. We will focus on the latter. So the hadronic light by light contribution can be further split into this kind of contributions. The dominant one is the pseudoscalar pole, which can be related with the transition form factors of 2 photons to neutral pseudoscalar. We have published a work on this subject, but we also have this kind of contributions, the meson box contributions, which are related with the pseudoscalar electromagnetic form factors. This is an ongoing work with Angel, Adnan, and Pablo, and yesterday there was a talk concerning these form factors. So let's recall a few facts about QCD. And this is characterized by two emergent phenomena. Confinement, which entails that the fundamental degrees of freedom, quarks and gluons, are not isolated in nature, but they form hadrons instead. And the dynamical generation of mass, that quarks and gluons acquire masses dynamically in such a way that the proton mass mostly comes from QCD rather than the Higgs mechanism. Both phenomena are tightly connected with the QCD running coupling. As you know, in a large momentum regime, in the ultraviolet regime, the coupling decreases and perturbation theory is a powerful tool. But as we approach the infrared domain, the coupling increases and saturates. Perturbation theory is no longer an option. To tame this non-perturbative character of QCD, we can employ a continuum method called Dyson-Schwinger equations. There are no assumptions on the coupling of needs derivation. These are not restricted to a certain domain of current quark masses. We can study pion and heavy quarkonia at the same time. And very importantly, is that hadron observables can be traced down to fundamental ingredients, namely propagators and vertices. The downside is that these form an infinite tower of coupled equations. For example, the quark Dyson-Schwinger equation, the fully dressed quark propagator is written in terms of its bare counterpart, the fully dressed quark gluon vertex, the fully dressed gluon propagator. Each of them obey their own DSEs. So a truncation scheme is needed, but we often follow symmetry principles to systematically truncate the system of equations. Just a little advertisement is that DSEs are a promising tool for QCD and hadron physics. There are many predictions available these days regarding form factors and distribution amplitudes, parton distribution functions. Now we are reaching generalized parton distributions as well. And of course, the mass spectrum. So the starting point to study the meson form factors is the quark propagator and the meson beta-salpeter equation. So we have seen that the quark propagator is related with other objects, but this fits onto the beta-salpeter equation as well. And we need to know very precisely the interaction kernel that occurs between the quark and the anti-quark. So again, this is an infinite set of coupled equations that must be truncated. We will use symmetry principle to truncate it, namely Ward-Green-Takahashi identities. And the leading order symmetry preserving truncation is the so-called rainbow ladder truncation that consists in replacing the fully dressed quark-gluon vertex by the bare vertex and compensate with an effective interaction. Consistently, the Bethe-Salpeter equation is truncated like this. So although this is a very simple choice, it is sufficient to ensure charge conservation and very, very importantly, the appearance of pions as the Goldstone bosons of QCD. Among other things, this ensures this manifestation of the Goldstone theorem that says that pions exist, the left-hand side of the equation, if and only if dynamical chiral symmetry breaking is realized, if the mass function is different from 0. For the mixed states, such as the eta and eta prime, we include the so-called non-abelian anomaly directly into the Bethe-Salpeter kernel. So this particular form, which can be represented like this in some way, ensures that we can get the flavor mixing. So to calculate the form factors, we notice that the rainbow ladder truncation is self-consistent with the impulse approximation. Namely, form factors can be written in terms of triangle diagrams. In the triangle diagrams, we have the quark propagators, the fully dressed quark propagators, the meson Bethe-Salpeter amplitude, and the quark photon vertex, which can be written in terms of the quark propagator dressing functions. Similarly, for the electromagnetic form factor, again, we have the same ingredients, propagators and vertices. So every hadron observable is traced down to propagators and vertices. So now we show some results concerning the pion transition form factor. Our main result is this black line. We can reach arbitrarily large space-like momenta. Within the same formalism, we can ensure that the abelian anomaly is satisfied, while also recovering the asymptotic limit by Brodsky-Lepage. As you can see, there is a precise agreement with the low and the intermediate range of momentum data, and with the assumption of a bar, which we can conciliate with a bar data at large values of Q squared. However, this data from a bar favors a flat top PDA. This is in contradiction with our modern understanding of how the PDAs should look like. So now, concerning the eta C and eta B, well, eta C is this black line. Again, we are comparing with the only available data, VAVAR, and NRQCD results. And in blue, we have the eta B. We have to compare with. So now we display the results concerning the eta and the eta prime, the green bands. As you can see, we can reach very large values of Q squared. And the agreement in this region is remarkable. So there are extra subtleties in this case, but we can handle them. And as an important point from the DSE approach is that to produce these form factors, we don't need to fit the curves to any set of data. Actually, the only phenomenological input that we need are the decay constants and the masses. And therefore, we could produce all of these results. So now, with the results at hand, we need to parameterize them in order to use them as inputs to evaluate the light-by-light contributions. BMD and LMD have been popular for some time, but this failed to recover some of the asymptotic limits. And we have seen that Canterbury approximants are a new optimistic alternative. This is a rational representation of the form factors that enable to recover both limits, the low and the large square limits. And we don't need to use higher order representations. We can just cut it down to the x square variable, to the momentum square, power 2. So finally, putting all together, these are our results for the pole contributions, the pion, the etas, eta C, and eta B. And as you can see, the size of the eta C contribution is more or less the size of the error bands here. So in the future, it might be a good idea to recalculate these kind of things. We compare with other DSC approaches, for example, the pion, pretty good agreement. And well, this is just to caption the standard model value. Now, concerning the box contributions, I just want to mention quickly, this is the well-known result for the pion form factor that yields to this value for the box contribution. And the beyond rainbow ladder truncation was presented yesterday, I think. And this is the value that we obtain, and a slight increase in the absolute value of the contribution. We can also get the kaon and the rainbow ladder and beyond rainbow ladder truncations, and the same pattern is obtained. And as compared with other results from another DSC group, well, our approach seems robust because we are within the same range. So finally, I would like to conclude by saying that it is a good time to revisit the computation of mu, specifically from the hadronic contributions. And particularly, we have calculated the light pseudoscalar pole contributions, and for the first time, the heavy pseudoscalar pole contributions. We notice that the eta C part might not be neglected in the future. And with this approach, we are perhaps the first group that gives results from a beyond rainbow ladder truncation within the pseudoscalar box contributions. And very importantly is that the approach we have followed unifies a variety of hadron structural properties. I mean, many other objects that are in agreement with their corresponding experiments and sophisticated lattice simulations have been obtained within the same approach: form factors, PDAs, PDFs, and GPDs. So finally, the DSC treatment allows us to trace down the observable subpropagators and vertices, maintaining the connection with the theory. So we believe that this can be useful in the collective effort in the future. And thank you.
Great and on time. Thank you, Kepani. Questions for Kepani? So, if I may ask, the excitations of the eta and eta prime, are we sure these are negligible or not?
Excuse me, Pablo?
Yeah, the excitations of the eta and eta prime mesons lying around 1.5 dB or so, all these excitations, are we sure that they are negligible or we don't know yet?
This is hard to say within this formalism because we can study very well the ground state pseudoscalars, but concerning the excitations, well, this is another topic and it's kind of difficult. So I can really tell you what we will get.
As I understand, nobody knows yet. So Edgar, please.
Hello, thanks for the talk. In your final point on your conclusion, you say you can compare with collective effect, right?
Yes.
Okay, so how is this? How can you explain it?
Yes. For the hadronic light-by-light contributions, the standard model result has taken into account the phenomenology and the lattice. And I think that they have also taken into account one of the Dyson-Schwinger equation results from another group. And what I actually mean is that so far this approach has not been considered enough like a promising approach, and the fact that there is only another group contributing to this endeavor. So okay. If we see that that following different DSE approaches, we arrive at essentially the same results, the community might consider this as a robust formalism to contribute to these efforts.
Okay, so and finally, you can compare with measurements from the experiment, right? Something like the spectra, a ratio, or?
Yes, one strong point of this is that the only input from experiment we need are the masses and decay constants. No other inputs.
Okay.
So this is kind of strong.
Okay. Thank you.
Pablo, you have your microphone turned off.
Oh, I'm very sorry. I had it open only on the other. I'm with two apps, so I was in the other device.
No worries.
Okay, so again, now we will have Dr. Sebastián Rosado talking about opportunities for exotic signals at the LHEC within the 2Higgs doublet model of type 3. Please, Sebastián, can you start sharing your slides? Sebastián? Can you all hear me now?
Yes, I can.
Yes.
Okay, so I'm checking for Sebastián. I don't see him in the audience. Maybe he's having some problem right now. So what shall we do, Jose?
So he's the last one, right? In the session.
Yeah, Mick is already here.
Yes. Does anybody know where Sebastián is?
Can anyone from Puebla make him a quick call?
I mean, okay, if he's not here, we're gonna have to continue with Mick.
Okay, so Mick, can you hear us? Can we hear you?
Yeah, I hope so. And you should be able to see me as well.
We are glad. Okay, so now we will have the last invited plenary talk of this meeting. Nick Mulder from LHCb, from CERN, will be telling us about a very, very hot topic now, as it is rare decays and anomalies at LHCb, a potential violation of lepton flavor universality. Please.
Yeah, thank you very much. Let me share my screen. So you should be able to see the slides, just to check.
Yes.
Okay, good. So indeed, yeah, thank you very much for the nice words, and maybe I can also say a bit in Spanish, just to say muchas gracias por su introducción y por invitarme a este congreso. Disfruté mucho y estoy honrado que puedo dar la última charla o también podemos esperar tal vez por Sebastián en un momento, pero por ahora aún tengo que dar mi charla en inglés.
Thank you, Mick.
Yeah, something.
Go ahead. Yeah, go ahead, because we don't know where Sebastián is. So, and also I want to thank you for being connected the entire meeting. Okay.
Yeah, I really like to make a bit of connection to the Mexican society, let's say. So it was nice to be connected and to follow all the different talks. Now I should start. Okay. So indeed, I'm going to tell you a bit about rare decays and anomalies at LHCb and the potential violation of lepton flavor universality that we have seen. And basically in the picture here, you can see one of the events with such a rare decay in our beautiful LHCb detector, I can say. You might have heard, let's say about 2 months ago is by now, some things about a potential leptoquark or a new force of nature, machine, the general at BBC challenging the standard model, and just taking one more close to home for me from the Netherlands, our group leader at NICAF there saying this is why he was already doing research for 25 years. So you can imagine, you can wonder what is all the news about and why are we excited while remaining cautious, because of course we need to express the proper caution about how significant the results are still, and yeah, we still need to confirm some of it. So I try to show you a bit of that today. So firstly, rare decays. Rare decays are loop level decays that are mediated by the weak interaction. So it's a type of flavor changing metal current in that sense. And they go via this transition that is very strongly suppressed in the standard model because of those loops, but also because of CKM elements and sometimes even the GIM mechanism. And this makes them really perfect for indirect discovery, because even a very small contribution can have a large effect on these rare decays. So for example, there was a search for K-long to mu already quite some time ago, when they just knew about the up, the down, and the strange quark, and they didn't find it at the level they expected. And later, quite soon after, let's say, realized that this could be resolved by including the charm quark, which had a negative interference, and we only saw the decay quite a bit later. And for example, also the mass of the top quark could be bounded already with BB bar mixing before the top quark was found itself. So in that sense, rare decays have historically shown to their value, and we are looking at rare B decays, and we've started to see some anomalies there. So rare B decays, in that case, we talk about a B quark going to an X quark or a D quark potentially. In the case of the D quark, you have a bit of a suppression with another CKM factor. And additionally, there is a production of 2 leptons. So these are really precise tests of the standard model with the 3rd generation of matter. And also in this case, you have loops, namely either a box, as here on the top, or a penguin, which is a bit difficult to see, but you can see it when you manipulate the diagram a bit. And both of these have branching fractions of the level of 10 to the minus 6 or less in the standard model, so quite small. And what you can have is a new particle. So you can have a leptoquark that directly couples the bottom particle and the muons, or you can have something that couples directly the B and the S quarks, like a C prime. So this is the places where the kind of things that we can possibly be sensitive to. And these anomalies that we see in the rare B decays, we see them in quite a few different modes. So this is just to give you an impression. I haven't introduced quite some of the concepts yet, but the main point is you see all of these predictions in colored pictures, basically, and you see the data that are deviating. And these are measurements from our run 1 data, so 14, 15, but also up to 2020. So we still see some deviations. And today I want to tell you more about the most recent measurements. So when we see these anomalies, we of course ask the question, is this consistent with each other? Because if the results in the different measurements are at very different sizes, then of course that doesn't make sense. So what we do is we use this effective field theory at the B hadron scale now. And this is similar to, for example, the beta decay, which you could approximate with a 4-point interaction as well. And similarly here, we integrate out the heavy degrees of freedom, and we get this directly 4-quark operator, basically, with certain coefficients and operators. And to be precise, those couplings and operators are described by this kind of effective Hamiltonian with operators OI and associated Wilson coefficients, and we group them by the leptonic current. And there's basically 3 ones that are relevant for the standard model. There is the photon that you can have if you have a dilepton mass that is close to the photon mass, so 0, you will see surely effects from that if allowed in the decay. And otherwise, For a more pure, let's say, B to SLL transition, you care about the C9 and C10 coefficients, which are associated with vector and actual vectors. And outside of the standard model, you can also have scalar or pseudoscalar transitions, or you can have transitions that have the opposite core current handedness, which would be marked with this kind of apostrophe. And when you then look at the data of those anomalies that I just showed you, what you get is you get something like this here. So the standard model is at 0, 0. There's no new physics, let's say, but the data combined from LHCb, but also from the other experiments, you see that there's quite a significant deviation, specifically in C9. And these are 1, 2, 3 sigma contours, so it's quite a big one. And perhaps there can be something in C10, but that depends a bit on which modes you look at. And yeah, I will get a bit more into detail on that later. So what is the detector we use? We use the LHCb detector, where we look at B hadrons specifically with high precision, and we do this by putting our spectrometer configuration basically in the forward direction from the proton-proton collision at the LHC that takes place around here. Then when the tracks go through the spectrometer, we have a very good momentum resolution that allows us to separate BCPS and BD decays. We have also an excellent charged particle identification, so we don't have too much background, even for these rare decays, when we have to identify muons or electrons. And finally, we have a clear separation. If you zoom in around the collision vertex here, you can see the proton-proton collision point. And for example, for BCPS to mu, one of these rare decays, you can see after a few centimeters, basically, quite a clearly separated decay vertex. And this is essential to reduce backgrounds coming from 2 B decays that could be combined to form fake rare B decay candidates. And then there is one part that falls a bit almost on the detector side that we need for 2 of the measurements I talk about today, namely the branching fraction of the B sub S to mu and the branching fraction of B sub S to phi mu. Namely, we produce many different types of B hadrons, and we need to know those their branching fractions, but we need to do those relative to a B0 or B plus mode, because we have the branching fractions from the B factories. Then what we measure ourselves is the efficiency corrected yield that you can see here on the left. And we want to know, of course, a branching fraction ratio like here. So we need to know this factor here that's called Fs over Fd or Fu. And this is the B sub S over Bd, or you could also say B plus production ratio, because we are assuming throughout this talk and in general at LHCb that Bd and B plus are produced at more or less the same rates. And additionally, for QCD, also FSFD is interesting as a probe of hadronization. And we've seen kinematic dependencies on PT, but not on eta of the B hadron. So what we do, this is a very recent combination, is to measure this production ratio by having modes that have a prediction of the branching fraction ratio. And the recent part is that we do a combination where we determine a single value from all the previous measurements with higher precision. And the point is those previous measurements have been done at the main LHC energies and the full LHCb acceptance. 2 of them, they actually come with these branching ratio predictions, the one here on the left and in the middle. And then you can really say something about the scale of FSFD. And in the case of this B to J psi X modes, you just say something about the dependence. And what's essential is that we were able to update external inputs. For example, thanks to a BEST3 measurement of the D sub S branching fraction. And this really gave us a significant improvement in sensitivity. And yeah, this fit that we did was a bit complicated, so I cannot give too many details. But the main point here is that the uncertainty on this ratio of production rates is reduced by about a factor 2, down to 3%, 3.1 to be precise. And we measure 2 common B sub S branching fractions, the J psi phi and the DS pi branching fraction, with a similar precision. And especially this first one, the J psi phi, is essential for the BS to phi mu, and FSFD is essential for B sub S to mu. And additionally, in the side of, let's say, the hadronization, we do see some interesting things. but it's difficult to get a consistent picture of the PT dependence out of our data. So future predictions from theory on especially the PT dependence would be very useful in order to improve that description. So on the rare decay side, all the results that I'm showing you are new and really from the last few months. The oldest is from December last year. And they're all with the full run 1 plus run 2 data. So there's the improved measurements of B2mu decay observables, RK with the evidence for lab universality violation, and some supporting measurements, let's say. And I will also give some interpretation and conclusions along the way. So firstly, we have these leptonic measurements. So in this case, the quark basically that comes out in the transition actually is in the initial state. And that means that you can make still very good, precise theory predictions, even when you want to look at the branching fraction. And then there is a certain effect in the standard model called helicity suppression, which means that these modes are very rare in the standard model. So for example, the B sub S to mu mode, which is the one that is really in the experimental reach now, is only happening 3 in a billion times, basically. And the BD to mu, which is another time CTM suppressed, only once in 10 billion times. Now this mode is sensitive to C10, so the actual vector contribution, and we can use it to distinguish scenarios with or without C10 contributions then. And additionally, scalar contributions could have very large effects here because they don't have this helicity suppression effect, and they would be enhanced relative to the standard model. And these scalar contributions I don't discuss too much today, in the sense that for that, a very nice mode would be to look at the dilateral mode. And in the dilateral mode, we expect a very small standard model. So anything we would see now, and given the beta mu that is so close to the standard model, anything here would be related to new scalar contributions. So then beta mu and photon radiation. One thing that we've included now in this new measurement is something called initial state radiation. So when you have this diagram of a B sub S to mu, you cannot avoid that there can be photons that are radiated. And if they're radiated from the initial state, actually you get a mode that is sensitive not just to C10, but also to C9, so to vector and actual vector contributions. And we refer to this as B to mu gamma throughout the analysis, basically. And the new observable is that we search for this while we do not, in the mode where we do not reconstruct the photon, and basically for dimuon masses in the region that we can look. And you can see the kind of shape that that has. So you can really see, because you missed the photon, it almost looks like a kind of a background like the semi-leptonic decay of the pion without measuring the neutrino, obviously. And then the other part that we always were taking into account is the red here, and that's final state radiation. So if there would be no radiation from the beta mu diagram, you would just have the Dirac function of the dimuon mass, but you cannot separate that. And those soft photons that you can get from the muons, they will make that you actually have a bit of a radiative tail. And this we simulate with a certain package called photos, and otherwise does not really affect the measurement or the theory predictions. Previous measurement of beta mu have been done not just by LHCb, but also by Atlas and CMS. And we've made a combination that we published last year. And there is a bit of a mild tension here, which is compatible with having new physics, not just to C9, but also to C10. So at least from this combination by itself, you would tend to think there is something happening here. And for the initial state radiation mode I just introduced, there is no search yet. So we are really the first. And then beta mu, in terms of analysis strategy, what we do is very similar to before, but we strongly improve the calibration. And the strategy itself is basically to look for those dimuon pairs that can be consistent with a beta mu, but we don't look in the signal region yet. We blind this region, as you can see here. And what we actually do is, you can see at first we have a lot of backgrounds. So these are all signal candidates, basically. And we have to train something that you can see around the x-axis, which is BDT, multivariate classifier that is designed to look at decays that come from 2 B hadrons in the same event, and that actually mimic a mu candidate. And these happen very often. but you can see that our BDT works very well to reduce them at high BDT values. And then how we get our result is by fitting both to the invariant mass and to the BDT. And one thing I should mention is that we do include also some cuts on the particle identification of the muons to make sure that we don't have too much background from regular BDKs. So when we do this fit to the mass of the dimuon pair and the BDT, what we do is we divide the sample in BDT bins. And what you then actually see in the plot here on the top right is that the background is combinatorial, is too much in the first bin. But as this is a strongly falling shape, we can just exclude the first bin, and then we have a few bins where we are sensitive. For signal, we have something that is more or less flat, which is by construction, but still we need to determine if that signal shaping data actually remains flat after our full selection. And we now have a new procedure where we use simulated samples. We correct those with data control channels for all the effects that we know are not fully 100% well simulated. And we then do a cross check with our B2HH data, and we see that they are consistent at a very good level. And this really reduces the uncertainty significantly, because before we were taking this red distribution that is limited by the statistics of the data, basically. So we know how our signal is distributed over BDT, but we also need to know the shape in those BDT bins in mass. And the mean we can calibrate the momentum scale basically with regular BDKs, even if they go to hadrons. The resolution we calibrate with germanium and upsilon resonances going to muons, and then we interpolate between the two to get something that fits more with the kinematics of our signal basically, given the similar muons. And then the FSR related tail parameters from the radiative effects we calibrate on simulation, taking into account that the resolution we find in the data is slightly worse than that we have in the simulation. And we even take into account that the mass shape varies slightly with the BDT bins. So we know how our signal behaves in the two fit variables, but we also need to know how many candidates we expect in that full range. And for that, we use two well-known channels, which are complementary to each other. So we use B2J-K+, where you have muons in the final state, which means that you have a similar trigger MPID to the signal mode, but you have an extra kaon and slightly different kinematics at the start. And you have BDK-Pi, where the decay topology is very similar. So the starting kinematics are similar, but then the trigger and the PID, those make it more difficult to compare. And the nice thing is that by doing this with both these modes, we have a comparison also of how sensitive, let's say, our efficiencies are to these things, and we can actually do a cross-check with them. So given that we have measured the yields in these two modes, we can basically convert the yield that we see in the full range of the dimuon invariant mass and BDT. We can convert that using the normalization yield and branching fraction, using the relative efficiency of the normalization and the signal, and the relative production ratio of those two modes, where this FSFD from the new combination really helps reduce the uncertainty for the B sub S. The signal yields that we see over the full BDT range are consistent with the improvement that we would have expected. If we just look at the normalization part, and we also do an important cross-check with these two normalization modes, and we see that with the PDG, they are consistent, and actually naively our precision is better, but we didn't optimize, we didn't do the full systematic procedure. But still, it's very encouraging to see that two different modes are very consistent with each other. So we understand our signal, we know their shape, we know how many we expect, but we also need to consider backgrounds. For this combinatorial background that we train the BDT against, actually we cannot generate enough simulation to model this in our data. So we have it as a free exponential shape over the full mass spectrum. And luckily we have enough data that doesn't have other backgrounds at high mass, so that we have an independent handle to determine it. And that makes it even more essential that at low mass, we really calibrate carefully all of the different B hadron backgrounds. And one especially important one is the one in pink here, the B2HH. So all of these, we take simulation samples, we do a lot of calibration there, and it's especially difficult because mis-ID doesn't happen often at LHCb. So actually, it's even difficult to keep enough data to do the calibration. We do a cross-check with B2H data where one hadron is misidentified, and we are still consistent within 10%. So that's all fine, and we can calibrate, and we can have a look at our fit. And you see that the B sub S to mu fit has a very clear signal. The uncertainty is similar to the combination I showed you previously, and the two other smaller signals that we look for, given the backgrounds that we have, we cannot yet confirm them. And even in the case of the B sub S to mu gamma that is new now, we have a negative fluctuation. So we have a better limit than expected. If you then look again at the compatibility with the standard model, you might remember this combination was at a bit of a tension with the standard model, but the internal LHCb result, let's say, or the LHCb result by itself was never at a very strong tension, and that remains the same. And we just have clearly reduced uncertainties. That's the main message, basically. And we also put limits on the two modes that we don't see. And they are as expected, given that one has an over fluctuation and one has an under fluctuation. There is, however, one parameter in specifically B sub S to mu that I should also mention. So neutral B mesons, they have mixing, and they propagate just as CP odd or as CP even eigenstates. And only the CP odd one should contribute to beta mu in the standard model, which is given by this parameter, then A delta gamma is +1. Now, the nice thing is that for B sub S CP states, basically, there is a very big difference between the decay width of the CP odd and the CP even. So what we can do is we can measure the lifetime of the B sub S to mu decay, in the case of the B sub S decay at least, to test if there is some CP even contribution. And that could really show new physics, even if that is not obvious from the branching fraction measurement itself. Previous measurements were consistent with the standard model, but very dominated by statistics. And because this is a B sub S to mu measurement only, there is a separate optimization. So we remove those backgrounds that you just saw. We take a smaller mass window, and we can loosen our particle identification requirements. And the procedure here is to do a fit to the two bins, the one at the top and at the bottom. Then you have a background subtracted data sample, and then we just need to determine how our efficiency depends on lifetime, and this we validate with data with B2H decays, BDK pi and B sub S to KK to be precise, and then we can do a fit to the lifetime distribution. And that fit looks like this. You can see the acceptance here at low lifetimes is a bit worse, because that's where you get a lot of these random combinations of particles, this combinatorial background. But otherwise, everything looks okay, and we get a lifetime that is still compatible with the standard model, and it's actually even a little bit less compatible with non-standard model cases. And actually, the message remains that we need more statistics to really make a big improvement, because still the statistical uncertainty is a factor 10 more than the systematic one. So then we can switch to the semi-atomic rare B decays. And these are actually regular rare B decays. So those anomalies I showed you, we've seen them in these rare B decays mostly. There's a lot of possibilities here because you have a spectator quark. So you can change and you can look at many different decays with many different B2S hadronic systems, let's say. And the physics that you look at here depends on the invariant mass of the dilepton state, which we call Q squared. So what you can see is that actually you have contributions from 3-level transitions to the J-psi mode. So this is actually a CC bar state where the CC bar goes to the 2 muons, the normalization mode from B to mu, you might remember. And what we're actually interested in is this rare mode, but we can only look at it in certain Q squared regions where those 3-level transitions are not too big. And this also affects theory predictions. So also in these J-psi and Psi2S regions, the theory predictions are not so precise. And in any case, the branching fraction of such a mode is already difficult to predict. As you saw the uncertainties, the angular observables are better, but still tricky, and there's still discussions on the theory side. But if you do measurements of relative branching fractions between a di-muon and di-electron mode, or differences in angular observables between those modes, then you really get a clean test of the standard model. That's what everybody agrees, basically, also on the theory side. And that's exactly what I show you today, this RK result where in basically outside of this, in the standard model, the only difference that you would expect here is the fact that muons just have a larger mass than electrons. And so if you look at a large enough Q squared, large enough invariant mass, then the ratio of the branching fractions of these modes should be equal to 1. The uncertainty on this prediction comes from QED and is only the order 1%. And there's work ongoing to make this uncertainty more precise, because this was a more or less rough estimate when we were still at the 15% experimental uncertainty. This measurement is sensitive to C9 and C10, but only in muons relative to electrons, because it's a ratio of the two. And the point is that any significant deviation we see here would be a clear sign of new physics. So today I show you the update with the full run 1 plus run 2 data. And one thing I do want to mention also is that there have been previous measurements. So we've done a measurement with run 1 with the B0 to K star mu over EE mode. And there we see something that is clearly not 1, which is about 2.5 sigma per bin. And yeah, a bit bigger deviation also in size than what you will later see in RK. And we have done this measurement with a baryonic system. And there the precision is a bit worse, but also there the deviation is on the right side, let's say. Another thing that is important to mention before we go into the RK measurement itself is that measurements with electrons at LHCb are not so simple. So they provide this extra challenge because when they interact to leave tracks, and also with our Cherenkov detectors, they will leave some Bremsstrahlung. And if this Bremsstrahlung is emitted before the magnet, then it will affect the curvature throughout the magnet, and we will underestimate the momentum. So what we do is we look for the Bremsstrahlung that was emitted, because we do have a good angular resolution before the magnet. And if we can find those clusters, then we can correct the electron momentum. But this can happen only about 50% of the time. And even when we do that, or even in the end, let's say, using both cases where we can find this cluster or when we do not, we still have a worse mass shape. And this is what you can see here. On the left, you can see the muons with a range from 5200 to 5600. On the right, 5200 to 5600 would be a kind of range from here to here. So you can see that clearly there's a much larger energy loss here. And that's also why you see these partially reconstructed backgrounds turn up in the dielectron case. And additionally, electrons are more difficult for the hardware trigger because the electronic calorimeter is just much more busy. So we have electron samples that are triggered in a few different ways and not just by the muons as we can do in the dimuon mode. And the strategy to measure RK is to measure it as a double ratio. So we do it relative to the J-psi mode that for theory is not nice, but for experimentalists is very nice to do as a calibration. We do a double ratio because we don't want to be sensitive to the absolute electron and muon efficiencies. And what we then do is some things that are very similar to beta mu. You do a selection to reduce combinatorial with this PET. You do some specific cuts to reduce B-hadron backgrounds. And you make sure that your rare and J-psi mode are selected identically, except for the fact that they have a different dielectron invariant mass to reduce any differences there. Then yields are determined from fits to the invariant mass, and efficiencies you get from corrected simulation. So it's essential that you validate all these points with cross-checks. And first I want to show you the mass fits to the calibration mode. So you can see really the amazing statistics that we're getting and how clean we can look at these calibration modes. And this enables us to do very precise tests and very precise calibrations, basically. So the first cross-check is to actually do look at the single ratio and the absolute efficiencies of muons versus electrons. We know that this ratio of the J-psi modes of the branching fraction should hold within 0.4% to be equal to 1. But what we see actually, what we see is that it does hold and it holds within about 2% given our current statistically and systematically mostly limited sample. This is compatible with the expectation, even if you divide in subsamples or you look at different trigger categories. Then we can also look at the JSI measurement differentially. So you can divide the JSI sample for muons and electrons in different variables to make sure that the efficiency actually transfers from the JSI mode to the rare mode. That is the thing that we are actually concerned about in the end. And we even look at variables where the distributions are quite different, like the lepton opening angle. And we see that even if we take the largest observed departure from the flatness, let's say, that we expect after correct corrections, the bias on RK is only 0.1%, so very small even compared to the theory uncertainty. Then, as an independent validation of the double ratio procedure, we do a measurement of the ratio with the Psi2S mode. And this result is well compatible with Unity. We get a very clear Psi2S peak, as you can see, with not too much background. And actually by itself, this is the most precise test of lepton universality in the Psi2S decay. Although, of course, the measurement has not been optimized for that. Then, given these cross-checks, we are happy to have a look at the RK, and we do this from a fit to both these rare modes, to the K-mu mass and the Ke mass, and also to the JSI modes, the fits that I showed you before. And then we take the uncertainties on these efficiency ratios as a multivariate constraint included in the likelihood. And you can see also that the ratio of the EE mode and the mu mode is about a factor 2. So that mostly comes actually from the trigger. And that is something that will improve in the future after our LHCb upgrade. The results that we are getting now are ironically getting exactly the same central value as before, which was with data up to 2016. You can see it here. And the main systematic uncertainties, although they are small, it's good to say that they come from the fit model and from the statistics of the calibration samples, even for this kind of rare decay now. The compatibility, we then determine taking into account uncertainty on the standard model prediction by integrating the profile likelihood that you can see here in the plot on the bottom right. And what we find is evidence of lepton universality violation at 3.1 sigma. So that's a very nice result that we managed to find, let's say. And additionally, a nice result that you can also get from here is you can look at the absolute branching fraction, given the fact that we have a measurement of the dimuon branching fraction itself. And we see, actually, as you can expect from the lepton universality measurement, where, just to be clear, this is muons over electrons, so we are seeing more electrons than muons. You can see also here that the deficit is not really in the electrons. That's still consistent with the standard model, but the deficit seems to be in the muons. And then we can go back and look at the effective field theory. So there have been already quite some updates by theorists in that regard. And if you first consider that there's only new physics in the transition of B to S mu, and you look at these new clean results, the RK and the B sub S to mu branching fraction, you can get, just with those clean results, already a pool of 4.7 sigma that either points towards C10 or C9 minus C10. So there does seem to be something happening there. Then you have these other B to S mu observables that have a bit more discussion. I guess that's why they are in orange. And they by themselves also have a pool of 5 sigma. And you can combine them with something that is more or less consistent between all the measurements. And you get a pool that is even a bit larger. So these are all different scenarios, but they indicate all in a more or less consistent way new actual vector or vector contributions to the B2S mu transition. Are there any other options? Well, there is a bit of a slight inconsistency in the sense that the B2S mu measurements only, the angular and the branching fraction measurements, they deviate a bit from these other clean observables. So that can be explained if there's a universal contribution to the C9 to the vector transition. That would affect also B2SEE somehow, and that then C9 minus C10 is only affected in the B2S mu transition. And this is slightly favored 6.4 sigma compared to 6.2 sigma in the B2S-mu only case, let's say. But it is an interesting scenario for theorists, and I also think it's interesting because it can be linked to some other anomalies that we're seeing in B2C tau mu when you look at the standard model effective field theory. And I don't have time to go into detail here, but yeah, that's in the backup. And you might wonder about other recent results. And I don't know if I have enough time to discuss those because
yes, please go ahead.
Okay. So first there is B2S-2 mu, which was first shown 2 weeks ago at the standard model at the LHC conference. This is the case where you have an S spectator pore basically in the decay, and the run 1 result was at the 3 sigma tension. If you look at this specific bin at least, we do also here an update to the full run 1 plus run 2 data. And a similar strategy is used to the RK analysis, but because you're just looking at the muons here, you do a single ratio compared to the J psi decay in this case. And this here profits from the improved uncertainty from the FSFD combination I showed you earlier today. And the results here are that the central values are quite similar. You can see the gray, the old result, and in black, the new result. And the uncertainty is reduced by more or less a factor 2. I should even say the gray here is with already the updated FSFD, so the previous uncertainty was even a bit worse. And the systematic uncertainty, I note the physics model that can be improved, but it's not a limiting uncertainty. The main limiting factor here, I would say, is to understand better the form factors, because you can see in blue this light cone sub-rule prediction, and in red the combination of that with lattice, which cannot say too much by itself, as far as I understand, at this low Q-squared region, but apparently in combination suggests quite a strong deviation. So I'm really looking forward to a better understanding of these form factors of this transition, basically, and to see what this will do in these global fits to the effective field theory. And then we have this angular analysis of the B plus to K star plus mu mode. This is a bit of a complicated one, so I think the main point that I want to make here is that this really is the first full angular analysis of this mode. The difficult part here is that the K star plus decays always to at least some neutral particle, so either a long-lived K short, which is the mode we looked at, or you would have to have a pi zero, which would be even more difficult for us. And then there is a dedicated fitting strategy to deal with non-resonant contributions. There is this kind of decay angle, how do you say it, description that actually is not too different from the Higgs to 4 lepton that we saw yesterday. And then they do a procedure basically to determine as much information as possible from this decay. And the variable that most people are then interested in is this variable called P5 prime. And you can see that compared to the theory predictions, there does seem also here to be a bit of a deviation, although uncertainties on this specific mode are large. The main point is actually to not just look at one variable, but to look at the consistency with the standard model, taking into account all the different measurements in these 8 observables. And that finds something that is inconsistent at the 3 sigma level by itself. I do have to say, given the small uncertainty, or sorry, the large uncertainties in this mode, this is probably a bit overstating, let's say, the inconsistency in this specific mode. But especially if you combine this with our update from last year in the K star 0 mu mode, where we have more sensitivity, we see that the consistency of the total fit improved. And basically the take-home message is we also do these branching fraction and angular measurements in addition to the clean measurements. And they paint a consistent picture with some possibility for a slight change, whether you take the C9 universal fit or you just say there is some B2S-mu change, let's say. So in summary, these rare B2SLL decays are a sensitive probe of new physics. There's many observables, and you combine them through these global fits to Wilson coefficients, which suggests a consistent set of anomalies. Today, I've presented to you branching fraction measurements of B2S modes that reach a new level of precision, aided by this measurement of FSFD that we brought out recently. And of course, the headline is that we have an evidence of Lepton universality violation in RK. There's also additional and consistent constraints from angular measurements. And in regards of prospects, we have many measurements underway right now of lepton universality ratios. So you can see all of the different strange hadrons that are naming, let's say, these ratios, many angular analysis, and also we're looking for modes with taus, although that's more difficult. And our upgrade is ongoing. We will increase our luminosity by a factor 5 and remove the hardware trigger that limited the electrons. So we will gain another factor 2 for electrons. And yeah, there's many more results from us still to come. But for now, eso es todo, amigos. Thank you.
Okay, thank you very much, superb talk. I have an urgent question, but let me see if somebody else has a raised hand, because I should ask first. Yes, yes, of course. Please, Wolfgang, go ahead, please.
Yes, thank you for the nice talk. I wonder, you're constantly referring to effective field theory, which, if I understand it correctly, is essentially a Fermi theory with 4 fermion vertices. But this has in particular a problem at high energy, and you're actually involving heavy masses. So are you not worried about some uncertainty coming in from that side?
I mean, it depends, I guess, on at which level you call it high energy. So I think the assumption that is made when we do these effective field theory bits, let's say, is that the physics comes in at a high enough mass. So basically at something at the electroweak scale or above, so that we are not too, how do you say it? That we are not too affected by things like that. I don't know if that answers your question or if there was something else you wanted to point out.
No, just if this is under control. I mean, if the deviation from the exact standard model is considered, if this is under control, or.
I think the main concern that people have in that sense is not so much with the EFT formalism, but more with these hadronic uncertainties. So maybe then actually the easiest plot to show for that is an anomaly plot I started my introduction with, is the fact that we can make predictions. Oh, sorry, almost there. Okay, it just shows, but the main point is we have these different uncertainties, and I just showed like this. And the main question is, how large should you actually estimate those uncertainties? And that is a larger effect, seems right now, at least, than the conceptual part of the EFT.
Okay, thank you.
Okay, thank you, Wolfgang. Any other who wants to ask before me? I don't see anyone right now. Let me ask my question. So can we see your SMF discussion of B to C tau nu together with the anomalies you discussed?
Yeah, I have to say I hope I didn't put too much information in one talk, so I had to cut something. And then so the point is that there is this measurement not just with the rare decays, but also with the semi-leptonic decays. And there you don't really expect anything, but there are measurements where you look at the C to tau nu transition compared to the muon or the electron transition. And there's measurement not just of LHCb here, like in the rare decays where we are dominating, let's say, but you also have Bell measurements and Babar. And this combined average here in red deviates from the standard model by, I think now it is 3 sigma. So it's a bit less because it's one measurement by itself that shows this. And the thing is that somehow this can point towards these kind of lepton quark solutions that are coupling more to a 3rd generation and less to the 2nd generation. And here it becomes a bit full, but the main point is that if you introduce one lepton quark at this electroweak scale, you can find something that explains why you see a relatively large effect in such a semi-leptonic decay, because such a large effect in semi-leptonic decays, I think before these deviations was never expected. and why at the same time you see a smaller effect in B2SME mu and this universal contribution to C9 as well. So it explains all of these deviations in one go, let's say.
Okay, thanks again. I would like to insist on something on page 49. Well, I don't see other raised hands. So in this beautiful plot you show in the previous slide, yeah, here. So one can easily realize that having Bell data is extremely important to assess the possible size of the deviation with respect to the standard model. So do we need to expect for Bell 2 to reach really competitive errors with yours in these anomalies you discussed at length or not? Or what do you think on that?
That's a very good point. So indeed, in this case, you can see that even with, I mean, Bell has of course less B hadrons that are produced, but they have a far cleaner environment and they have the nice fact that they produce them at the same time, let's say, so they can use they can tag with one side and then measure the other side. So I think Bell 2 should beat us at some point in this measurement unless we really manage to do very well. In the rare case, the limitation will just be the statistics. So we are hoping that Bell also there, Bell 2 can really provide a strong constraint, but currently it seems that they might get to the level where we are at now with LHCb by the end of their full run. So the kind of measurement as like RK, the precision that we have now in RK, they expect in 2026 or something like that. And maybe just to add, we are really hoping that Atlas and CMS can contribute in this. That would be very nice.
Sure, absolutely. Okay, thanks a lot again. So yes, there is a question by Edgar. Please, Edgar, go ahead.
Okay, thank you. First, I have like a little bit of doubt. Maybe okay. Yes, for the precision of this branching ratio, you make correction for the efficiency, right, from the Monte Carlo, and that is that will put like a little bias and when you compare with the standard model, because you correct the standard model and now the final result you compare with the standard model, right? It's not like, I don't know, it's yeah, more or less. You understand my question? Especially okay, when you calculate this, all this, you reconstruct all these B masses or different branching ratios, you identify the particle, but you make the correction for the efficiency, right? If the efficiency is coming from the Monte Carlo and the ratio and how many expect and how many you measure, right? But this Monte Carlo was generated in terms of the standard model, right?
Yeah, exactly. So what you are assuming, and that's an important caveat in that sense, it's good that you mention it, is that we are generating with the model of the standard model. And then so also when you have, I mean, you see these deviations in the angular measurements, as far as I know, when we then do this measurement of RK or RK star, given that we haven't had a, 100% confirmation of deviations, there is no change. We just assume the standard model efficiency, let's say, when we make this estimate here. And in that sense, the biggest caveat I think that you can make is if there would be some change in the shape of the Q-squared distribution or some change in the angles that could affect the efficiency and somehow affect the estimates here. But that would still mean that there is something different with respect to the standard model.
Okay, so as you say, so there is not something fishy is linear between one another. So if there is a scale factor, so okay, it's the same, it's no problem, right? That is the assumption.
When we talk about C9, C10, let's say about these Wilson coefficients being different, then the effect should be that basically the shape shouldn't change really. So the efficiency, the efficiency wouldn't change actually. It would just change the total amount by which you would see one mode relative to the other.
Okay, thank you.
Okay, thank you very much. Now there are no more questions, so we thank a lot Mick again. First, thanks a lot for this very nice talk and discussion.
Sorry, Pablo, I'm sorry. I don't know if we still can ask.
If you want to ask a question, please go ahead, Arturo. Yes, sure.
Okay. Well, first, Mike, thank you very much. It's a wonderful talk. My question is about this last line, what you have there. So you have a very interesting result, a 3.1 sigma, and there is no more data to analyze, right? So it's
Well,
so
after the update, yes, but
we need to wait
not in this
until.
mode.
Sorry?
Sorry, indeed, there is no, this RK result is not going to, we have the full run 1 plus run 2 data. So we are waiting for the upgrade before we can update this again. Yeah.
Okay. Okay.
But
yeah.
the important point is that we do have other final states. So we will, of course, be updating these. So this measurement here on the left is with run 1 data only. And we're actually working on a measurement of this RK star together with RK simultaneously, because the point is that the K star EE can be a background, a partially reconstructed background where you miss the pion in the K plus EE final state. So this is really the thing that we are in LHCb very much waiting for an update of this one. And then also other ones are being worked on.
Okay, thank you. Thank you very much.
Okay, thanks a lot to both of you. And now, thanks again to Mig. I want to insist on that. It was a pleasure having you and the talk and the discussion. And then, since this is the end of the meeting, I want to thank all the speakers in this session, all the speakers in previous sessions, all participants, and of course, the organizing committee, Jose, Karen, Arturo, Irais, Marco. Thanks a lot. And now Jose will be talking.
Hello. ¿Sí me escuchan?
Yes, we can hear you.
Yeah, thanks. Okay, so as Pablo said, we are at the end of the meeting, at the end of the program. And I don't know if there's any remaining questions on today's scientific program, let's say. If anybody wants to say anything. Otherwise, we can go to the, I want to show some closing, a brief summary and some acknowledgements. So you can see my slides.
Yep.
Okay. So this is a very brief summary of the meeting, which took place in the last 3 days. In terms of participants, we had 140 registered participants in the Indico, of which we had almost exactly 50% participation from students, and the rest were professors. And we had order of 80 connected in Zoom daily, or up to 80, let's say, and up to about 15 on Facebook. So I think we had a very good participation overall. And in terms of presentations, we had a total of 49, of which 9 were invited talks, 23 contributed talks in the program, and 17 posters, which were uploaded in the YouTube video playlist, as well as 2 tributes. And I'd like to thank again all of the invited speakers, because it takes some work to prepare all of that material. Make is still here, Alec, I think. And they came from many places around the world. So I think it shows a very good interaction with the with the rest of the countries. And then, of course, the session conveners, which helped keep everything organized in time from the different institutions in Mexico. We had some awards and election results. Congratulations again to Professor Adnan Bashir for the 2020 DPyC medal. We had 3 students with the poster awards here listed, Fabian, Paulo, Edwin. And we have a new vice president of the division, Juan Barranco. So congratulations. And then, of course, we have some people who were in the committees, which I cannot list here, but they also did a lot of work behind the scenes to organize all of the elections, the vice president, the medal, and the poster judges. So it took quite a bit of work. And we had, of course, a lot of support from technical, administrative, and design, which I list here. For example, Jesus, who is here, has been all the time enabling Zoom from very early to late, the recordings and live stream. And Marco helped us a lot with the Facebook and YouTube pages, which were very useful. Then we have people who helped in the registration and fees. Patricia and Alfonso, not here, but they were very essential for the meeting. And of course, people who helped maintain the Indico, the mailing lists, and the design for the page. Thanks a lot for all that work. Okay, we have here, I want to show the group photos that we got yesterday, and these we will post on the Indico page. We'll add another page there to show this group photos. Thank you for showing your camera during the group photo. And okay, there was another set where you were supposed to do something crazy. Okay, if you go back and forth, you can see yourself change a bit, not too crazy. And I wanted to say here, if you're not yet seen the Facebook page, please have a look, because all of the recordings are there. You can go to the videos tab, and then you will find all of the recordings. Okay, and finally, thanks for your participation, and see you at the next event on behalf of the organizing committee. And at this point, I think Karen, Arturo, Marco, Irais should say something if they can, if they want to. And this is the end for me. Thank you.
Thank you very much, Carlos. Thanks to you. You did a really good work organizing all this.
Thanks to everyone. Hope to see you next year.
Yes, thank you very much, everybody. Thank you, Jose, as well, because he was a great organizer. And also thanks to Irais, Marco, and Arturo, and also to all the attendants and participants. I don't know if it will be another session of break rooms, I don't know, but it could be worth to discuss with the speakers of this session. But again, thank you very much, and we stay in touch.
So we could keep the Zoom open for another 10 minutes maybe, or if people want to stay connected, probably yes, and you can talk to your friends.
Okay,
so officially, I think.
Thank you, everyone. Thanks to the organizers.
All right. Thank you very much to everybody. Bye-bye.
Bye-bye.